Um, well, as you can see from the title, that I will be talking about classical integrability today. My main idea was to talk about integrable spin chain, which are quantum integrable systems, not classical, and explain how these things are related to gauge theories. But the thing is, so integrability is kind of a niche subject. I mean, it's a relatively popular subject and there's a lot of people working on it, but unless you have been working on something related to integrability, it may not be very familiar. It doesn't usually come up in standard undergraduate courses, for example. So probably I should first give some explanation about what integrability is, why these problems are interesting, and then try to explain how these things fit into modern research. So today I'm going to give a very elementary introduction to classical integrability. I will not say anything that's new or even modern. So if any of you has seen integrability before, what I'm going to say today may be very boring. So I'm sorry for that. But hopefully in a future talk, I will be able to say something more recent. And since today is supposed to be an introduction to the subject, if anything is unclear, just let me know at any time and I will try to explain as clearly as I can. Also, I should say I have never tried to explain these things to an audience before, so I'm not sure how clear it's going to be, so please ask questions. Okay. So what do I mean by integrability? Basically, it's as the name suggests, that an integrable problem is something where we can do integration. And the problem under consideration is solving equations of motion of any physical system. So these equations of motions are differential equations. And in principle, you find solutions by doing integration. And if you can solve the equations of motions exactly, roughly speaking, we can call those systems integrable. So let me give an example of what I mean. So a famously integrable problem is the Kepler's problem. You probably already know what it is. This is just a two-body problem. In three spatial dimension. This is the famous problem solved by Newton a long time ago, who was interested in planetary motions. What happens if two planets or two massive particles move in a gravitational field? So in three dimension, we know that the gravitational force between two massive objects is, let's say, something like this, where this is just some constant. So this would be G, M1, M2. R is the distance between the two objects. So say these are the two objects. This is R, the vector R. R is the norm, and R hat is a unit vector. All right, then this is the force between these two objects. And so what is the equation of motion here? The equation of motion is so something like this, where L is angular momentum. So L is something like theta is the angle in polar coordinates. And we know that we can solve this system. So basically, one common trick is that you change variable from time to the angle. And then the solution is that, so R as a function of angle is given by where E is some number. Energy, angular momentum, some constants, and so on. Basically, the point is that we can exactly solve this problem. So if you know how two objects are positioned with initial angular momentum at some given time, you can figure out what's going to happen at a later time. Now, what is an example of a problem that we cannot solve? It's just the immediate generalization. So you go from two-body problem to a three-body problem. So what is a three-body problem? You have three massive objects. So let's say choose some origin. Some masses. Now, the equations of motions are simple, so you can just write them down. Well, let's say G is 1. This is one of them. You have two other equations for R2 and R3. You find them by doing cyclic permutation. All right, so you have three equations. It looks very similar to our original problem of a two-body system. We just have one more massive object, but this system is unsolvable. Meaning, okay, so there's no known solution. There's no exact solution. So the two-body problem is an integrable system. The three-body problem is not. Now, this is kind of a motivation for what we mean by integrability. In reality, it is very hard to define precisely what we mean by integrability. Even in classical systems, we can kind of give a definition. In quantum systems, it's really rather subjective, and it's more art than science defining what quantum integrability means. It's mostly you find various analogy with the classical systems, which is why I want to give an introduction to the classical integrable systems, so that when we can generalize to the quantum situations, it wouldn't look so ad hoc. So the motivations are coming from equations that we see already in the classical systems. So with that in mind, let us try to define classical integrability. Basically, we want to mimic what was happening here, that we want to define systems that we can solve and systems we cannot. Well, so another example of classical integrable system beside the Kepler's problem is, for example, the simple harmonic oscillator, which we will encounter later. Any questions so far? To define classical integrability, I'm going to.
No,
Yes.
sorry, there was a question in chat. So
Okay.
I can just read for you because you are writing.
Okay.
So what does it mean by can't solve exactly? Is it like the solution exists, but we cannot express them using some nice functions?
Yeah, precisely. I mean, obviously, this is a well-defined equation, so there is some solution in principle, but we cannot write it in terms of known functions.
So as a complementary question, is it like anything which has a non-constructible solution is non-integrable like this?
Roughly speaking, yes.
Okay, thank you.
So for example, chaotic systems wouldn't be integrable in general.
Yeah, I mean, that's kind of another definition, I think, of integrability, which is not integrable is chaos.
I'm a little hesitant to make definitive statements because, as I was saying, it's very hard to make it very precise what integrable means. But yeah, that's it. Yeah.
Okay, so there is another question in chat which speaks like this: is there some Galois theory associated here?
What do you mean by Galois theory?
Maybe you can write in chat, Nian, or no, not to you, to the person who asked this question, or you can just speak whatever is convenient for you.
By Galois theory, I mean, I'm guessing that they're suggesting something like that we can prove that you cannot solve the quintic equation. Is it something like that?
Okay, let's have some time.
Well, I mean,
okay. So, yeah, he meant exactly this. Sorry, his mic is not working. It's okay. So
it's fine. Well, the flavor of the problem is the same, but I don't think the technology behind the arguments are different, but the motivation is the same. And I see another question: is it proven or a fact that we can't solve two-way problem? That's a good question. I'm not 100% sure, but I think it's known that we cannot solve it in terms of known functions.
Yeah. Okay.
Yeah. So in some cases, we know. I mean, if the differential equation is such that for that particular case, maybe you can prove that there's no exact solution. But in general, I don't think there's a characterization for which Hamiltonian systems have an exact solution and which ones do not. But case by case, the answer may be different.
So just as a complementary question, say for I have a first order ODE, and then we know that if you have initial condition, then you have a solution, at least locally.
Well, we know that it has a solution, but can we always write it in terms of simple functions?
No. So that's what was I going to ask. So of course we cannot always write like nice functions. So in that sense, these are not classically integrable, right?
I would say so, yes.
Okay. Okay. Yeah. Thanks for the clarification. So yeah, again, if you have any question, feel free to raise your voice or ask him.
Also, I know virtually nothing about analysis, so I may not be able to answer all differential equation related questions, but yeah, I will try to answer what I can. All right. In order to define classical integrability, I'm going to use the language of Hamiltonian mechanics. So a quick recap of the things that I will need is, so first of all, in Hamiltonian mechanics, we start with the phase space. So let's say I'm going to call it M, some phase space. Phase spaces have even dimensions. So I'm going to call it 2D, and we can always choose local coordinates such that, let's say, P mu, Q mu, where mu goes from 1 to D. These are my position coordinates, and these are my momentum coordinates. And the phase space is always a symplectic space.
Nafiz, sorry to interrupt
yes.
again. So there
no problem.
Another question in chat which asks, like, is it possible to find the graphical solution for three-body problem?
What do you mean by a graphical solution? You mean whether we can plot what will happen numerically? Yeah, we can do that.
Okay.
I mean, you can find numerical solution and then you can plot it. That's fine.
Okay. So Tofa, is it okay for you, or do you have more question about the graphical solution?
Yeah, I mean, just let me know if you have any more questions. That's fine.
Yeah, just feel free.
Yeah.
Okay.
Yeah.
Oh, okay, so it's okay. Yeah, please go ahead.
Okay. So as I was saying, that on the phase space, we always have a symplectic form. So a symplectic form, I'm going to call it omega. And we can choose local coordinates so that the symplectic form looks like the following. And I'm, of course, using the summation convention that there's a sum over mu. Is it clear what this notation means, or should I say something?
Clear, so just go ahead.
Okay, great. And so with this symplectic form, so if you have two functions on, so let's say f and g are two functions on the symplectic manifold, some real valued functions, then you can define their Poisson bracket, which is given by something like this. And in particular, if you take the local coordinates, this is the delta function. All right. So this expression depends on this form. So the coefficients here, so 1 and -1, these are coefficients that you would have here, for example. Okay. And in order to define the dynamics, we need a Hamiltonian. The Hamiltonian governs the time evolution of the system. So you all have a Hamiltonian function. Which is some function on your phase space. All right. Now let me define integrability, and then I will argue why this is integrable. And so this characterization of integrability was given by Liouville a long time ago, but I'm not sure exactly when. So it's also called Liouville integrability. So we will call such a Hamiltonian system Liouville integrable if you have functions on your phase space, exactly D functions on your phase space, such that they mutually commute with respect to the Poisson bracket. And all of them also commute with Hamiltonian. Okay. This property is called involution. And this just means that these functions are, or the values of these functions are constant with respect to time evolution, right? Because we know that, what do the Hamiltonian equations look like? So if you take some random function, then the time derivative of that function is going to be Poisson bracket of that function with respect to Hamiltonian. So this ensures that all these functions remain constant in time. All right. Now, the theorem is that the equations of motions of this system, by the system, I mean the system where we have these functions, can be solved. Now, the traditional language here is that it's called biquadrature. All it really means is that we can do integrate. I mean, we can do integration. We can integrate. Okay, now it's actually quite easy to prove this. So let us see how it works. We may not get to all the details, but we will get a feel for what the dynamics looks like. Okay, so we need to define some stuff. So first, let's define a one form. Let me call it alpha, which is just p mu dq mu. So notice that the information contained in this form is that d of this thing is, well, it's dp mu wedge dq mu, which was the symplectic form. All right. And then from RD, so d-dimensional real space, pick any point that you want. So let's say f1.fd. So these are just real numbers. So for any choice of such a point from RD, define a subspace over phase space. So this is the phase space, and we're going to define a subspace of this thing that we shall refer to as M sub f. So this sub f refers to this point inside RD. Let me call this whole thing f. And this is defined as follows. So these are the points in the phase space where these special functions that we were given their values coincide with these chosen numbers. So these are basically the level curves of these functions inside the phase space.
Yeah.
Yes.
Hello. So
yes.
Can you please explain like why we need these f mu's to be zero when you take the Poisson bracket between them? Like, is there any reasoning?
Yes, it will come up in the proof. I mean, I'm going to use this condition later to prove something. Yeah, you'll see. So for now, what I can say is that this will ensure that the dynamics remains constrained in some nice spots inside your phase space. I mean, in general, if I give you some random dynamical system and you start from some random point, then with time evolution, you will basically map out the entire phase space, meaning that you will go everywhere it's possible to go, right? Only by putting some constraints you can ensure that you'll be restricted to some nice parts of the phase space in a predictable way, and these constraints will help us ensure that. Okay, we will see this explicitly soon. Okay, the last thing I'm going to define is some function S, and the definition is going to be as follows. You start from some randomly chosen point inside your phase space, you integrate up to some other point inside your phase space, and the thing that you integrate is this one form. So this integration is taking place on a line. Maybe I can draw. Let's say this is a gray space. Well, actually, okay. So it's not just that. So the path over which I'm integrating, it belongs to one level curve. So Q0 and Q both belong to the same level curve. So let's say that this is one level curve MF. This is a point Q0, some other point Q, and you have to choose a path. Let me call it C. Actually, so let me make it explicit that it is defined with respect to path. Okay. So C goes from Q0 to Q. Okay. Also, something like this. Now, let us look at this function a bit more carefully. So as I was saying, that this path lies in a particular level curve. And how do we define these level curves? By these equations. So we say that these functions have this fixed value. Now, you can invert these equations and treat P as functions of Q and these Fs. Right? So basically what I'm saying is that P, and by inverting these equations for P, I can think of P as a function of Q and F. Now here by F, I mean the value of F. So basically these things. But I'm writing capital F because I'm saying that given any value of F or any value small f, meaning any value of capital F, you can do the system and write P as a function of Q and F. Okay. So here P is a function of Q and F. It explicitly depends on Q0 and Q. We're not going to worry too much about Q0. It's some choice of random point, but we will treat this S as a function of Q. So from this definition, it follows that S is a function of our path. Right? There's some path. If we choose a different path, there's no priori reason why you should get the same value of S. So it depends on the path, the point Q, this Q, which is the limit of the integration, and whatever value for the level curves we choose. All right. These are all the things that we're going to define for now. And okay, so an intermediate step. A lemma is that S is independent of C. So S does not actually depend on the choice of path. If you choose a different path, you will get the same value of S. It's not obvious, but we can prove it. It's not too complicated. So what will happen once we prove it? If you look at this function now, it's a bit weird. It depends on some variables Q and F. Okay, that's fine. So you have dQs and dFs. So it depends on two D variables. That's fine. But a choice of path is a more complicated object. So if you actually have a function that depends on a choice of path, then it's a complicated function. And it's not going to be very useful for us. But by showing this, we will have a very nice function that only depends on Q and F. Okay, so how do you prove this? So in which situation an integration over a line does not depend on the line and only depends on the endpoints? In general, that is the case when the thing that you're integrating is closed, meaning that this is equivalent to saying that d alpha is 0 on the level curve. Is this clear? I mean, there's some differential geometry involved. I'm assuming it should be somewhat familiar. All right.
Good for me.
Sorry?
It's good for me. I know this.
Yeah, I'm sure, but I was wondering about the students. Okay, right.
Well, I mean, please feel free. I can see there are a number of students, so please feel free.
Right.
Question.
Well, I mean, if nothing else, you can take it as a theorem that if you integrate a one form on a curve, then that integration will not depend on the curve and only depend on the endpoints if that one form is closed. Okay.
And can I say that, and if there is also no gauge freedom in the system?
What do you mean by gauge freedom?
Like think of the system of like the classical coordinate system, right? So like if we have integrated in over some closed path, would we have gotten zero, right? In the basic like Faraday's third law, right? Like curl of B minus D del B del T. If we integrate in a closed loop, you don't get zero, right? That's why we couldn't define a potential there. It's not.
Yes,
that's right.
Yes, that's right. But okay, so first of all, this integration is not over a closed loop. It is only over an open path. But you're right that, yeah, so if I move this over some other path that crosses through some singular points or something like that, or if you have some kind of flux, yeah, then there may be some path dependence. But there's no such thing. There's no flux or anything like that, or any singularity. Okay. Right, so this statement is equivalent to this statement. So this is what we're going to prove. Now, so before proving that, let me remind you that, so one property of the symplectic form is that, well, let's see. So I wrote down the Poisson bracket at some point of two functions. Okay, yeah, so I said that this is related to the symplectic form. So let me be, okay, I will do it. So on any symplectic manifold, such as our phase space, given some function, better to use a different. So given some function g, you can define something called a Hamiltonian vector field, which I will denote by xg. So xg will be a vector field on M, and the criteria for this vector field is that dg will be our symplectic form acting on this vector field. Okay, so this is the definition of Hamiltonian vector field. So here xg is Hamiltonian vector field of G. So okay, what does this mean? So this is a vector field. This is the two form. More concretely, so omega has two indices, mu. Well, actually, let me call it AB, and the vector has one index. Let's say A. So if you contract this with this, you're left with one free index. So that's the one form, and that is going to be del A derivative of G. That's all this means. Okay. And the consequence of this definition is that if you take two functions, let's say G and H, and you compute their Poisson bracket, then this is going to be equal to the symplectic form acting on the two Hamiltonian vector fields. So these are two vector fields. This is a two form, so this is a function, and this is a function. And in terms of indices, all this means is that, so you have A, B, X, G, A, X, H, B. You can break down these definitions in components. So for example, you can invert this and write X in terms of omega and G. And if you do so, and then substitute in this expression, you will find this expression with this choice. You can do it as an exercise. But this is the relation that we need. Okay, so the first thing that we note is that the Hamiltonian vector fields corresponding to these functions and involutions that we had. These things are tangent to our level curve MF. How do we see that? Okay, so first of all, what does it mean to be tangent? So our level curve was defined by constant values for these functions. So these vector fields are going to be tangent to the level curve if these vector fields act as 0 on the functions, meaning that if you move a little bit into the directions of this vector field, the functions do not change. But that is the definition of the level curve. So you're moving tangential to the level curve. Okay, so let's say that it's true. So xf mu, take one of the Hamiltonian vector fields, act on any of the functions in involution. By definition of the action of a vector field on a function, so this is the same as df nu acting on xf mu. And then by the definition of the Hamiltonian vector fields, this is the same as xf mu, xf nu. Oh, maybe there's a sign, but okay, doesn't matter. And then we just claim that this object is the same as the Poisson bracket. So this is the same as the Poisson bracket. So you find the Poisson bracket of these special functions. And this was already given to us as 0. So this condition now means that these Hamiltonian vector fields are tangent to the level curve. And in fact, these are all the tangent vectors to the level curve, meaning that they span the tangent space, because the level curves were defined by D equations in a 2D dimensional space. So the dimension of the level curves themselves were D. So dimension of MF equals D. And so how many of these things we have? One for each function, and we had D functions. So the dimension of the span of xf1, xfd is also D. So these vectors span the tangent space of the level curves. Here, of course, you will notice that I'm assuming some independence between these vector fields. I mean, they're not linearly dependent and so on. All right. Now, so notice that these are these vectors span the tangent space to our level curves. So let's say that this is a level curve MF. This is a point, and here the tangent space is spanned by so xf1, xf2, xf3, and so on. And we just found that omega, this 2 form, when it acts on any 2 tangent vectors, you get 0. So what does it mean? It means that omega is 0 on MF. Okay, but so recall that alpha was defined in a way that d alpha was omega. So this implies this is 0 on MF. So let's get back. So we wanted to show that S is independent of the choice of curve. It doesn't depend on which curve we choose. It only depends on the endpoints. And we said that this is equivalent to proving that d alpha is 0 on MF. And we have now just shown that d alpha is in fact 0 on MF. So then it is now true that S is independent of C. Okay, so we have proved that S is only a function of Q and the values of these special functions. Any questions so far? Okay.
Can you please say like what is your MF? I think I forgotten the definition. What is this MF? This manifold? Can you please repeat the definition?
So MF is a subspace of the symplectic space, of the phase space, where these functions have fixed values. So actually, maybe I can give an example here. Let's take the simple harmonic oscillator in one dimension. So what you have one position and one momentum, and the Hamiltonian is say half q squared plus p squared. So what is your phase space? So M is R2, spanned by Q and P. And so the dimension here is 2, right? So D is equal to 1. You only need one function, and you can simply choose Hamiltonian to be that function. Hamiltonian commutes with itself, so it's fine. And then what are the level curves? So the level curve, so MF is the set of points in R2, QP in R2, such that half Q squared plus P squared equals to, let's say, F. So what do these level curves look like? Let's say this is my Q, this is my P. Then the level curves are just circles, right? Of radius 2F. And the circle is my MF. Is it clear now what the MFs are?
Yes.
Okay.
Thank you.
All right. So why is this function useful? Because remember that we are trying to prove that a system where you are given these functions is integrable, meaning that we can solve the equation of motion. So we actually want to solve the equation of motion. And we are now going to use this function to define some special coordinates in terms of which the equations of motion will be very simple, and we will be able to exactly solve them. All right. So now, now let us define the new coordinates. So let's just take ds first. So what is ds? Recall the definition of S. So this was S. Then ds is, well, so first let's take care of Q. You take derivative with respect to Q. So Q appears as an upper limit of an integration. So you just get the integrand. Now we have to take care of F. So where is F dependence? F dependence is inside P. So because we were solving the level curve equations to get P as a function of Q and F. Well, so you find that right? So this is just the definition of how dx. Now let's just give this a name. So this is P mu dq mu plus, let's call this psi. So psi mu df mu. Okay. Now, whatever S is, if you apply d twice on it, so d square is 0, acting on any function, doesn't matter what the function is. So d square S is equals to 0. But what do you get by applying d on these objects? So if you apply d here, so you get dp dq, right? And dp dq was our symplectic form, dp dq. So from the first term, so we are applying d here. So from the first term, you just get omega. And from the second term, you get d psi mu wedge df mu. And this is 0 because of this. So this tells you that omega is the same as df mu d psi mu. There's a sign. I have absorbed the sign by commuting this thing. Okay, so what is the usefulness of this relation? So what we want to do now is that we want to change our variables from QP to psi f, right? We have the same number of these variables. We have from Q1 to QD, from P1 to PD, from F1 to FD, and from psi1 to psi d. Okay, that's fine. Now, this tells us that when we do this change of variable, the symplectic form does not change. I mean, the form of the symplectic form remains the same. Because what was the symplectic form? It was originally dp wedge dq with mu's. So basically d of momentum wedge d of position. What is it now? It's still the same. It's d of momentum wedge d of position. Well, so this simply means that when you write down the Hamiltonian equations of motions, they will look exactly the same in these new coordinates as they did in the original coordinates, right? I mean, the formal name for this kind of transformation is a symplectomorphism, but it doesn't matter. The point is that the equations of motions will look the same. All right, so let's look at the equations of motion. So what is the equation of motion for our new variable, the psi mu? The Hamiltonian equation of motion. So the time derivative of the position coordinate is the derivative of the Hamiltonian with respect to the momentum coordinate, right? So this one. All right. Now, so what can we say about this? So here, I should go back and point out that on a symplectic manifold, you can have at most d functions that are independent, that are functionally independent, and are in involution. Okay. Now, the formal proof will require some steps, but let me just try to point out why this is true. So recall that using this relation, we were able to show that omega, the symplectic form, restricted to the level curve, was 0. Now, on a symplectic manifold, subspaces of a symplectic manifold where omega, the symplectic form, vanishes are called Lagrangian subspaces. And you can kind of convince yourself that the maximal dimension of a Lagrangian subspace can be D. Well, it's related to the non-degeneracy of the symplectic form, which is part of the definition of a symplectic space. Anyway, the main point that I want to highlight is that there can be no more than D functions that are in involution. And notice that by definition, H was also in involution with respect to the Fs. So what that means is that H is not functionally independent of these Fs. So H can be written entirely as a function of the Fs. It can be a very complicated expression. All these Fs in some very weird functions. But regardless, you can always write the Hamiltonian as some functions of these Fs. Well, okay, so why is that useful now? Because we are going to take a second derivative of this equation and see what the acceleration is in terms of this new variable. So d square psi mu dt square is d dt del h del f. And here I'm going to use the fact that h can be written entirely as a function of the f's, so that this can be written as del square h del f mu df mu dt. Okay, so h doesn't have any extra time dependence that is not coming from time dependence of these functions. That's it. Now, this is 0. Why is it 0? Because how does the value of a function on a phase space change with respect to time? It changes by Poisson bracket with respect to the Hamiltonian. And by definition, these Poisson brackets were 0, right? This is df mu dt. Which means that this is 0, so this is 0. So what do we see here? We see that in terms of this new coordinate, accelerations are 0. So this is a very simple system. You have some position coordinates and some momentum coordinates, and your acceleration for the position coordinates is 0. So this is just like a free system, right? So so whatever the velocity is, it's going to remain constant with respect to time. There's no acceleration, of course, or anything. So what are the solutions of the equations of motions? The solution is that, hello, yes? Was there a question? Okay. Right, the solution is that of a free system, meaning that the psi dt, it's some constant, which were f mu's, and the acceleration is 0. Sorry, why am I writing like this? I should say that psi mu as a function of t is some constant, which is a position at initial time, plus just linear time dependence, because the velocity is constant, times the velocity. The velocity is del h del f mu. And this is a constant, it doesn't depend on time. And also, it doesn't depend on coordinates. So it really is just a constant. So this is the solution to your equation of motion. Completely simple, right? And in principle, we have solved the original system. So what is the trade-off? I mean, what did we have to do to be able to solve the problem? Because I mean, let's say that you are given a bunch of functions that are functions like these that satisfy these conditions, but they can be very complicated. And Hamiltonian itself can be very complicated. So then where did those complications go? So basically, all those complications have been hidden away inside these coordinate transformations. I mean, in order to find these variables, we had to use some tricks in differential geometry, right? So in practice, this coordinate transformation can be very complicated. But all this guarantees is that there is a coordinate transformation, assuming you're clever enough to find that coordinate transformation, that after the coordinate transformation, the solution to the system of equation is extremely simple. Now, if you want, you can go back to the original coordinates. Then the solutions will look complicated, but you still have a solution. So in this sense, we have constructed a solution given these constraints. And this is what was implied by this statement, that the equations of motions are soluble by quadrature. And this is why this system is called an integrable system. So any question? I mean, this is basically the bedrock of everything that I'm going to say later. Meaning this is the poster child of what an integrable system is. So yeah, if you have any questions or any confusion, we can discuss that.
So are there any necessary and sufficient condition for that sort of coordinate transformation to exist? Like when can we have such a nice coordinate transformation so that we have this nice solution?
Well, in principle, it's always true. I mean, it's not as difficult as finding a solution to a differential equation. No, but see, in practice, it may not be feasible to actually find the coordinate transformation. But yeah, I don't know what the criteria would be in terms of functions.
Such coordinate transformation always exists, may not be constructible.
Right. Well, yeah, but I would like to highlight that the situation is different from being able to solve a differential equation. For example, I mean, even if we know that a solution to a differential equation exists, we may not be able to say anything about what the solution is.
Yes.
This is more algebraic than analytic. I don't know exactly how to distinguish the two, but they're not the same class of problems.
I see, but I mean, for instance, this is Hamilton. So what we are doing in this context is solving Hamiltonian equation, right?
Right.
And this coordinate transformation is an efficient tool to solve any Hamiltonian equation in say classical particle mechanics, right?
Well, I mean, you can try, but it's all, I mean, you may not always be able to find the coordinate transformation. But so the existence of all these functions in involution implies that there is such a coordinate transformation.
Okay. So if those F exists having this involutive property, then
yes,
the coordinate transform exists. In other words,
yes,
you need actually existence of a Lagrangian submanifold.
Well, Lagrangian submanifold defined by these functions in involution, yes.
Okay. So naively speaking, if there exists a Lagrangian submanifold, which constitute your constraint of equation of motion, then okay, I see.
Right.
So yeah.
Yes.
Continue.
No, so I was going to say that, okay, so this is fine for the purpose of proving that you can solve the equation of motion. But so in practice, people use slightly different coordinates. But okay, so before saying what those are, maybe I can back to the example of the simple harmonic oscillator. So what was happening there? So as I was saying that a simple harmonic oscillator in one dimension, your phase space is just R2, parameterized by position and momentum. And your Hamiltonian is Q square plus R square, sorry, P square. All right. So let's say this is the phase space. So QP. And okay, so here the dimension is 2 times 1, meaning that D is equal to 1, and we only need one function in involution with itself, and we can choose as that function to be the Hamiltonian in itself. It is, of course, in involution with itself, and it commutes to the Hamiltonian because it is Hamiltonian. Then, so what are the level curves? The level curves are just defined by constant values of the Hamiltonian. So these are circles, right? So this is a level curve, F. And what do the dynamics look like? The idea is that, well, so as you can guess from this picture, that these functions do not change their value. So if you start in a level curve, you're going to stay in that level curve. And there is some choice of coordinates inside that level curve that changes linearly with respect to time. So how does that work in this example? So let's say that you start at some point on the circle here. Then in time evolution, you're never going to get out of this circle. So you are simply going to move around the circle as time progresses. So this is going to be the direction of time evolution for this point in the phase space. And furthermore, there is some coordinate with respect to which this time evolution will be linear. And the coordinate in this case is simply the angular variable, so the angular position of this point. So let's say it's theta. So theta in time will be simply some constant plus t and then some angular velocity. Sorry, it's not symplectic form. Some velocity. So you will simply keep moving around at a constant speed around the circle, round and round and round. So this is a periodic motion, as we already know, of course, right? But okay, so this is the essence of an integrable system. That, well, this is the simplest example, I think. but this picture generalizes, meaning that if you have a higher dimensional phase space and an integrable system, you can always find coordinates on the phase space such that you can foliate your phase space with toruses. So in this case, the circle is a torus, a one-dimensional torus. Okay, so when I say torus, I mean the product of a bunch of circles. So S1 times some product, S1. So if you are in a phase space of dimension 2D, then this torus will have D circles, right? So basically, your phase space will look like the following thing. M will have the following description. So there will be some D-dimensional space parameterized by the values of these functions, F1, Fd. So these are coordinates on this base space coordinates. And for each choice of values for these functions, you will have a level curve. And those level curves are going to be toruses. So this will be MF, where F is a choice of values for these coordinates. And if you start your dynamics from some point inside a level curve, then you will keep moving inside this level curve. Okay, I'll be horrible at drawing this, but okay, let me choose a simpler path that just goes around the task. Okay. But it doesn't have to be this as simple as this. I mean, it can go around the torus a bunch of times. It's fine. But the point is that it will be periodic. You will find some coordinates on the torus. So, for example, the triangular coordinates on a torus, they will keep changing linearly with respect to time. And if you start on this level curve, you will never leave this level curve. You will keep moving around in the same closed path. So the essence of the dynamics is very simple. It's a closed loop inside the phase space that we can completely characterize, given the information that which level curve we started from, given by the values of these conserved quantities, the functions that were in involution, and where we started, and then we have a closed path, right? Okay, so this is the physical picture behind a Liouville integrable system. And yes.
So I have a question about these functions F. I mean, for the example of simple harmonic motion that you have shown, the function is pretty easy, right? You have just chosen H, and H coming with H, that's 0.
Yes.
So I'm like, suppose I'm like, how do you, in principle, first come up from? I'm like, if you are given a non-trivial system, suppose I give you an inverted harmonic oscillator, then I mean, like the description you have put forward to find that final psi in terms of this simplistic, very simple form, it depends on finding these Fs, right?
Absolutely. Yes.
Right. So I'm like, how for a non-trivial system, so it is important that you find that F. I'm like, how do you know a priori what are those Fs?
You do not. No,
non-inverted.
There's absolutely no prescription that tells you how to find these Fs given a Hamiltonian. So if I give you a phase space, right, and a Hamiltonian, I have completely defined for you the classical mechanics, right? Because you can write down the equations of motion. So now, if you want to prove that the system is integrable, as you were suggesting, that you should try to find these functions.
Right.
But there's no general principle that allows you to do so. It is completely system dependent. You have to look at the system and figure out, and you may not be able to figure out. So what happens in the nice cases is that you may be able to show that the system has a very large amount of symmetry. So what is a symmetry? Symmetry is some group whose action commutes with time evolution, right? Right. Now, the symmetries are generated by some vector fields on the phase space. And associated with the vector fields, you have some Hamiltonian functions. these Hamiltonian functions are distinct from the Hamiltonian for time evolution, but these are Hamiltonian functions for the actions of the groups, symmetry groups, not the action of the time evolution. But anyway, and if those are actually symmetries, then those Hamiltonian functions will commute with Hamiltonian, right? So what I mean is that suppose you have some group G that acts on a phase space M. Then the generators of this group, let's say J, Ji, corresponding to these Ji's, you will have some Hamiltonian functions Hi. Or actually, I was using F, so let me keep using F. We'll have these Fi's. And the point is that these Fi's will commute with H, right? And these Fi's will also be a representation of the Lie algebra of this group with respect to the Poisson bracket. So you can choose a Cartan subalgebra of G. So those are some subsets of these Fi's. So let me call those Hi's. So they will commute among themselves. And furthermore, they will commute with H. So you can find some of these things if you have some symmetry, but they may not be enough. And you may have extra conserved quantities that are not obvious as a symmetry. I mean, they're symmetry by the definition that they commute with Hamiltonian, but you may not be able to find them easily from the geometry of the picture. Their action may be very complicated. So your best bet is to use symmetry. Try to find symmetry of the phase space. Other than that, it's a difficult problem.
Right. And is H in this Poisson bracket? Is it your central extension of your Lie group?
No, not central extension. It's the Cartan subalgebra. So in any Lie algebra, you have the maximally commuting subalgebra, right?
Mm-hmm. Mm-hmm.
So it's those things. So
no,
by definition,
in the upper part, H,
yeah?
Fi, in this first part. I mean, these H are not included. Right, these H. I mean, these H is not included in your Lie group, right?
No, this H is the time evolution. I mean, it's the Hamiltonian of time evolution.
Right.
Yeah.
That's what I was saying. So is this H your central extension of your group?
Sure. Yeah, you can call it that. Okay, I mean, in the sense that it commits with everything. So yeah. Okay, but this is not a conclusive anything. Right. I mean, it's a start. All right. So this was Liouville integrability, which says that if you have sufficiently many conserved quantities in involution with each other, then there's some coordinate in which the equations of motions are very simple. They look like a free system, and you can write down the solution. So this will be our prototype for an integrable system. And we would like to promote these ideas into a quantum mechanical system. Now, unfortunately, these ideas do not translate directly very well. So we have to slightly modify the characterization of an integrable system. So let me say something about how this modification happens.
Yeah, another thing.
Yes.
So suppose if you have a system, which have, suppose you have find infinite number of symmetries. I mean, is it guarantees that you can solve your system then? I mean, even is infinity enough to solve your system? Or what?
If you have infinitely many conserved charges?
Right.
Well, first of all, if you have finitely many degrees of freedom, then you cannot have infinitely many independent conserved charges. There will be, I mean, you can have, if your phase space is 2D dimensional, then you can have only D independent conserved charges. And that's enough to guarantee that you can solve the system, yes. However, if you have a system with infinitely many degrees of freedom, and then you have infinitely many conserved charges, that doesn't guarantee that you can solve the system. Because, well, I mean, you cannot really compare infinity with infinity, right?
I don't think I get that. I mean, why it won't be sufficient?
Sorry, what is the question?
I mean, why it can't guarantee me that my system is like fully solved. I mean, I can,
I mean, so the criteria is this: if dimension of phase space is 2D, number of conserved quantities is D, then it's integrable, right? Well, number of conserved quantities is always it always has to be an involution. Then it's integrable. Now, if you neither replace D with infinity, then the problem is that you cannot say that one infinity is twice another infinity. So this criteria doesn't make any sense. I mean, they're both infinity, but who knows which infinity is larger and by how much? And yeah, so that's one of the problems why we cannot use the Liouville integrability in case of, say, quantum field theories, because then you have infinite many degrees of freedom.
Right.
And so for that, we need slightly more sophisticated criteria. And so I have until 4:30, right? Is it right?
Yeah, you have.
Okay. Yeah, so let me try to introduce the tools briefly. And in a future lecture, hopefully I'll be able to use them to do some quantum stuff. All right, so the tools go by the name of lax pairs. Okay, so what are they? Basically, find two matrices L and M. Oh, okay, bad notation. That's unfortunate. Let's say L and X. Okay, so they are functions on your phase space, but they're matrix valued functions. So basically, so L and X are functions on M, but instead of being valued in the real numbers, they're going to be valued in. Okay, so for now, let me just say that they're going to be valued in the space of n by n matrices. Okay, I will be slightly more specific later. Now, okay, so find such matrices. Furthermore, they should satisfy the following equation. The time derivative of one of them is just the commutator with respect to another. So what I mean by taking time derivative of a matrix is that you just take time derivative component by component. So so L11 dot, L12 dot, L21 dot, and so on. And the commutator is just commutator defined in terms of antisymmetrizing matrix multiplication. All right, if you can find two such matrices, matrix valued functions on a phase space that satisfy this equation, then we would call them a lax pair. So this is called a lax pair. Okay, so what do they have to do with integrability? So notice the following thing. Define these traces. So let's say that On is the trace of the nth power of L. Okay. Then what happens? Well, so L was a matrix on a phase space, but this is just a number. So this is a function on a phase space, right? So this is a function on a phase space. And how do this function evolve? I mean, how do these functions evolve under time evolution? Well, you can just take the derivative. You take derivative as you would for any matrices. Right. Okay, so basically, so you had n copies of L, right? So L, 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 L with n in total. And then you take the time derivative and heat on each of them one by one and add them up. And using this relation, you replace each time derivative with the commutator. That's it. Now, is it clear that this is just zero? I mean, there's nothing to it. It's just the fact that trace is cyclically symmetric, right? You can cyclically permute whatever you have inside. And if you look at it for 30 seconds, you will see that you can always cancel terms term by term. I mean, first of all, there are even number of terms, right? Because so however many terms you have here, n, but you have 2 coming from the commutator, you can break them apart and match term by term to cancel everything. So this is zero simply because of the fact that this is a commutator, and other than x, all the powers are L's. So basically, you can put trace x L to the power n minus 1, and you have a sum with alternating signs, and you have equal number of positive and negative signs. Okay, so for a very stupid reason, the time derivative of this ON is 0, except that this is a very non-trivial equation. You have to find such matrices. Now, this is interesting. So you had a bunch of functions on your phase space that do not change their values under time evolution. So you have some conserved quantities. That's a good start. Now, so in case of Liouville integrability, we saw that there was a constraint on how many we actually needed to get integrability, right? So if we had 2D dimensional phase space, here. If I have 2D dimensional phase space, then I need D conserved quantities. How large of a matrix does L have to be for me to be able to find D independent functions? Well, if you don't know the answer, it has to be D by D. Okay, so let's not worry about that at the moment. The point is that if you can find such a lax pair, then you can construct a bunch of conserved charges simply by taking power and then trace. All right. So this guarantees that you have conserved quantities, but it doesn't guarantee involution. So we have to do something about involution. But before doing so, let me just point out that we can express the simple harmonic oscillator in terms of a lax pair. So let me do that so that it doesn't seem too mysterious. Simple harmonic oscillator, lax pairs. So here L is P, omega is, actually I was writing omega to be 1, so let me keep doing that. So we can write this as P sigma 3. Sigma 3 is the third Pauli matrix plus Q sigma 1, the first Pauli matrix. The second Pauli matrix. Now, if you look at this equation, the lax pair equation, that dl dt equals to ml. So if you break it down, you will find that this simply says p dot q dot minus p dot. This is equal to without the angular frequency, it looks kind of trivial. So let me just put omega. This omega is not the symplectic form, it's the angular frequency that appears in Hamiltonian of a simple harmonic oscillator. All right, now if you compare equations component by component, well, we have redundant equations, but two independent equations, P dot equals to this thing and Q dot equals to P. These are the equations of motion of the simple harmonic oscillator, right? So with respect to this Lax pair, this equation is just the equation of motion of the simple harmonic oscillator. All right. This will usually be the case. I mean, if you can find Lax pairs, then this equation will contain the information of the dynamics. All right. So now, how do we get to functions in involutions on phase space? So here, I will not be able to give you much detail, but okay, I can give you references later. Let me just mention the result. Okay, before mentioning that, let me specialize a little bit. So instead of this being valued in n-by-n matrices, let me put some Lie algebra here. Okay, so for example, this can be GLN, which are literally n-by-n matrices, but in special cases, it can be something else. For example, in case of the simple harmonic oscillator, sigma 3, sigma 1, sigma 2, they all generate the SU2 algebra, right? But I have an I here, so it's a complexified SU2 algebra. So it's SL2C. Okay, whatever, some Lie algebra. Now, let me introduce this notation that for any matrix X, I will say that X1 is equal to X tensored with an identity operator. And X2 is going to be an identity operator tensor X. Then the following is a theorem that these traces of things, they are in involution if and only if the following equation holds. L1, L2 equals to R1 to L1. I'll mention what R12 is, minus R21 L2. Now R12 is an element of Lie algebra tensor Lie algebra. So recall that L is valued in Lie algebra. L1 is valued in Lie algebra times identity. So this whole thing is valued in Lie algebra tensor Lie algebra. This whole thing is valued in Lie algebra tensor Lie algebra. So this equation is valued in this vector space, and R21 is a permutation composed with R12. So basically, so let's say this is a Lie algebra. This is a Lie algebra. We take some element from the Lie algebra. Suppose you take U from here, then you put U here, and you take V from here. You put V here. So this is the permutation matrix. So you end up with an element that's also valued in Lie algebra tensor Lie algebra, but you have just solved the elements. Okay. So if you can find such an element of G tensor G, such that this L satisfies this equation, then and only then all these functions that were conserved will also be in involution. Okay. The proof of this is somewhat non-trivial. You can just believe it for now, or you can look it up. This R12, this object is called an R matrix. Not a very imaginative name. Now, if you want to check that the simple harmonic oscillator is in fact integrable in this sense, then the R12 for the simple harmonic oscillator is the following. H here is Hamiltonian function. Omega is the angular frequency. Sigma 2 tensor L. L is as before this thing. So sigma 2 is valued in SL2C, L is valued in SL2C, so R12 is valued in SL2C tensor SL2C. And it's a function on your phase space, right? Because H depends on P and Q. And you can check that with this R2 and this L, this equation is satisfied. Let's see. So I am out of time. And since I will talk another day, I will not take any more time right now. Let me just try to motivate a little bit that why we want to go in this direction. So notice that we originally had a formulation of integrable systems in terms of a bunch of functions in involution. Now we are saying that that formulation is equivalent to this alternative involution. Sorry, this alternative formulation where we have two functions called a lax pair that satisfies some simple looking differential equation, and a somewhat complicated looking equation. Okay, so here you may be a bit confused about what this bracket means. So it is the Poisson bracket, but these are matrices. So they are actually defined as follows. So L1, Ij, L2, Jk. So these are components of these matrices. So they are just ordinary functions on a phase space. You can take the Poisson bracket, sum over J. So I and K are free indices. So this is going to be the Ik component of this thing. And these are just ordinary matrix commutators, so there's no mystery there. Okay, so then I'm saying that if you have this lax pair, and furthermore, if you have this R matrix satisfying this equation, then this system is completely equivalent to a Liouville integrable system. The benefit of this system, however, is that we can generalize it to infinitely many degrees of freedom, and we can quantize this. Now, there are also attempts that you can make to quantize the Liouville version of integrability, as I stated there, but that will get into some, well, symplectic geometric stuff with Hamiltonian reduction and so on. This is actually easier to quantize because you already know how to quantize a Poisson bracket. You replace the Poisson bracket with operator bracket, right? So that is what we're going to do here and promote this to an operator equation or some modified version of an operator. There can be order algebra correction that we cannot see here, but the basic idea is that we will promote this to an operator equation, and these will be operators acting on the Hilbert space of some quantum systems. And then this equation with the modified version of this equation, that's what we'll call a quantum integral system. So we will use lax pair to quantize our classical integrable systems. And we can also use lax pairs to define integrable quantum field series with infinitely many degrees of freedom, because here we are not really saying anything about how many degrees of freedom you have. I mean, you can be careful, but you can also be less careful. Okay, so let me end now for today, and we will pick up another day. Are there any questions? Oh, I think Ashrat sir has a question. Hello.
Asha sir, do you have any question? Please feel free to unmute yourself and start.
Maybe he's not here.
Okay, but maybe he can ask when he's here. So
yeah, sure.
Nafiz, for your beautiful talk, and if any of you have any question, just feel free to.
I have a quick question for Nafiz.
Sure.
I wanted to see the gauge theoretic picture from out of what you talked about. So it seems like you have a principal G bundle type of thing, and your matrices, these objects are taking values in the Lie algebra of the gauge, something like that. So so in that case, is the base manifold the phase space?
Let's see. So that will depend on a little on how I phrase things.
Yeah.
But so in that language, basically what will happen is that you will find that the phase space is going to be the modulus space of G bundles on some Riemann surface. But that will,
yes.
So I will have to introduce a bunch of other stuff that I have not really talked about at all today. I mean,
okay, so what is the phase space? Yeah, so what is the phase space in that case? Is the modulus space of flat connections or something like that?
No, it's not the flat connection. It's a modulus space of G bundles itself is a symplectic space. Well, actually, it's a hyperkähler space, and it's called a Hitchin system. So it has a canonical base and a vibration. But I mean, yeah, I can talk about it in a future talk.
So maybe I interrupt a bit. So Nafiz will give another talk 2 weeks after from today, when he will talk about this quantum field theoretic and more research talk. So
I think Asha sir was trying to ask a question, but yeah, I couldn't hear Asha sir.
Sir, we could hear you. You may just write in chat, and I can just read out for everyone.
Okay, am I audible now?
Okay, yes. I
discovered what happened. My microphone was turned down rather low, so nobody actually was hear me. So I was muffled out. Your Laxpere thing, I mean, it just sounds somehow reminiscent. I mean, let's say I am completely oblivious of everything. It looks like flat connection condition, right?
It is.
You can
yeah. Mm-hmm.
So is it that what is actually going to pursue, that you actually try to embed all these lag spares inside some flat connection equations and try to solve them out?
Well, yeah, you're right. So basically, there's a picture where you can represent an integrable system in terms of just G bundles. So it requires introducing some extra data. You have to introduce a Riemann surface, and you can show that the Laxpere condition boils down to that Riemann having a particular type of G bundle on the Riemann surface with some connection and some extra field called the Higgs field. Doesn't have anything to do with the Higgs particle, but also called Higgs field. And then basically, you can show that the phase space becomes the same thing as the moduli space of that G bundle. And then the dynamics are constrained. Well, yeah. Your dynamics, you can describe it as dynamic inside the moduli space of G bundles. Although I wasn't actually planning on talking about that, because I mean that's a purely classical picture. It's just that so far what I have said about the Laxpere, it seems a bit ad hoc. Okay, where this matrix is coming from and so on. So that picture with the G bundle, that makes it very natural that why this structure exists, the structure of a Laxpere exists at all. So, I mean, if you're interested in geometric interpretation of these classical integrable systems, then yes, it's a very nice, it's a beautiful story. And it becomes relevant again if you want to study supersymmetric gauge theory and their vacua, because you can show that in certain gauge theories, the space of vacua are exactly the same as the moduli space of those G bundles. So they are, again, classical integrable systems. It's a wonderful story, but I don't know if I will have time to talk about it. What I had in mind is simply to go to integrable spin chains, which are much simpler things. Just a quantum version of what I talked about today.
Yeah, I mean, the Laxpere is basically a one-dimensional evolution equation.
Yeah.
That actually it should be down to something even simpler rather than going to Riemann surfaces. So I was actually contemplating, I mean, how does the spin chain actually enter this game? Apparently, I mean, I expect you would be talking about this in next talk, but I was getting a little bit impatient. So
no, yeah, it's perfectly fine. So yeah, I don't think, I mean, the introduction of the spin chain is not natural in the sense that you just have to introduce the spin chain. I mean, you just have to say that your quantum system is defined on a product of a bunch of points. Your space is a bunch of points with some vector space assigned to each of them. So the Hilbert space is a tensor product, and you have some Hamiltonian that defines maybe some kind of nearest neighbor interaction or slightly less nearest neighbor interaction or something like that.
Is this where you are
yes. So these are matrices that I was drawing. So right. So these tensor products that I was introducing, they are going to be components of that spin chain Hilbert space. So different component of the tensor product will come from different spin sites.
Right?
I'm sorry.
Is this picture that you actually have this theorem written out is only for two spins? Is that how you're thinking about it?
This one? Oh, well, yeah. Yes, but this is local, so it doesn't matter if you have more things around. I mean, you need two spins for this theorem, yes.
You're going to actually promote this to some Yang-Max equations, right?
Exactly, yes. Yeah, so in that sense, the spin chain is very natural because that's actually a physical system, right? It's the Heisenberg spin chain, so it's the simplest model for a magnet. So yeah, if you are already motivated by the condensed matter system, then okay, then you can start from the definition of the Hilbert space and Hamiltonian. But then it may not be very motivated to define integrability there because it's not obvious what a quantum version of integrable system should be. But you also happen to know what integrability is in the Liouville sense, then you can quantize that and get to, again, the Heisenberg spin chain.
I see. Would you recommend one or two, more up-to-date reviews on this thing for entry point? But I know you are going to give the lecture.
Yeah,
but,
so
you'll be giving this next lecture in 2 weeks or 1 week?
I think 2 weeks.
Yeah, it's in 2 weeks, and next lecture will be an hour late than our regular time because Nafiz has some other meeting. So it will be at 9 p.m.
We have a few, point us out to some references that we can actually play with before we listen to you
actually,
again.
so let me give the reference for today's talk, so which is about classical integrability. So let's see. So okay. So this is for classical integrability. Let me see. And so for the picture about how to rephrase the Lax pair criteria in terms of G bundles, there's a very nice review. So let me find the exact title. Okay, so that it's a review article. It's not an archive. So let me give it the title. By Hitchin. Actually, sorry, this is the original paper. I mean, it's very nice, but sorry, maybe I can give something a bit more review-like. Okay. There's a short book by, well, also Hitchin, Siegel, Ward. The title is Integrable Systems, but it has a subtitle which is Twistors, Loop Groups, and Riemann Surfaces.
By the way, the modular space in this case, it's a finite dimensional space?
Yes.
It is, right?
Yeah.
Okay. So before taking the moduli, it was an infinite dimensional space. When you go to the moduli space, then it becomes a finite dimensional space, right?
Yes.
I mean,
right. I mean, yeah, if you just consider the space of connections, yes, that's infinite dimensional. That's right. But once you question out by the gauge transformations, yes, you get finite dimensional space.
Right. So, what is reference that you mentioned is by Hitchin?
It's this book. So it's a very short book, and also this book has 3 parts. So the first part is written by Hitchin, I think, which is which is called Riemann Surfaces and Integrable Systems. So that chapter is enough for the connection with the G bundles.
Okay.
And yeah, this is one of the most beautiful articles about this integrable story I have ever read. It's wonderful.
I wanted to mention one book. I'm sure you're familiar with this book, Hamiltonian Methods in the Theory of Solitons by Fadeb and Takhtajan.
Yeah, of course. Yeah, it's a very classic book. Yes. Yeah, I have.
A very good book.
Right. Yeah, but I have the book, but I haven't read it very carefully. Yeah, well, maybe I should. Right, and for the quantum picture, I don't know yet which reference I will use, so I cannot give an exact title, but what I will try to find is something along the line of the following. Now, there are many lectures on algebraic Bethe ansatz. I'm sure most of them are fine. I will just pick one of them. For classical integrability, the problem is that there are many books. There are like 500 pages each. So no one has time to read those things. So this is a short review that's also nice. And this is also short and very nice. And these are usually short, so that's okay.
Okay, so are there further questions, comments? So if not, then I again re-announce that the next talk will be also by Nafiz on the continuation of this beautiful topic after 2 weeks from today. And it will be 1 hour later than our usual time. So to be precise, is at 9 p.m. and Dhaka time, because Nafiz has some other meeting. And yeah, if you have any question, please feel free.
Yes, and I will try to send the reference before the talk. Well, I will decide which one I'm going to use, and then I will send an email.
So if there is no further question, let's thank the speaker once again, maybe virtually.
Oh, okay, you can clap. We can clap.
Okay, yeah.
Thank you very much, Nafiz. Thank you.
Thank you. Yeah, it was very fun talking to you.
So I'm here 10-15 minutes more. So if you want to talk informally,